Sorry,
Sorry.
go ahead.
So yeah, our third speaker this morning is product marketing director. He's over 25 years of expertise in SoC design and verification, focusing on the product marketing and management for Cadence's Xcelium simulator. His career includes roles at Arteris, Synopsys, Compaq, now HP, of course, Intel, and Cirrus Logic. Paul holds a BSEE from Texas A&M, and the title of his talk, again continuing the theme, is AI and GenAI for verification productivity.
Thanks, Mike. Much appreciated. Good morning, everyone. And Hemendra, I appreciate your presentation this morning. It's going to be a great intro for where I'm going. So really what I'm going to kind of build on the concepts that Hemendra talked about and kind of show how we're actually applying it to EDA tools and what we can do with this. So, all right. So I think Hemendra had a slide similar to this. Really, the issue that we're dealing with right now is how do we scale everything? So complexity is continuing to increase. We're having more and more design starts. And then we have this slight problem of being able to scale the number of engineers needed to get all this work done because the amount of data is just exploding. So what can we do about that? Well, traditionally in our industry, we've seen things evolve quite well. We have these magnitude leaps in productivity where, in the original, it all started with manual circuit design. Then we went to automated transistor level design. And then that leaped to cell-based design. And then for most of us, we've all seen the RTL design. I mean, that's kind of where I think we've all been sitting in this industry. And each one of these improved the methodology, gave us a big leap forward. And the tooling itself also evolved to meet these goals. So where we're sitting now, though, is we're kind of at that point where we need to go and find that next big leap forward. What can we do? And that's really where we're seeing the potential for AI to come in and make a really big impact for us. So if we kind of just look at an overall strategy from Cadence's perspective and what we're doing. So first off, we're working with AI, but it's not that we're just going to blanket everything with AI. You have to do it in a nuanced way. There's certain places it makes sense and it can provide capabilities. So first off, if we take the engines, what we're having to do is think about how we're going to need more compute to be able to do the AI, because really what we're doing is trading off human-powered time for that of the CPUs to do more effort. And I should actually go beyond CPUs. It could be GPUs, it could be custom silicon, all of the above. And that's how we're scaling our software, where it can run on basically all these platforms, ARM, x86, custom silicon, FPGAs, et cetera. Now, those engines themselves aren't necessarily going to be replaced by AI. Really, what we're doing is augmenting the technology, and to the end user, it's just another algorithm. What we're doing underneath the hood, we may be using an AI engine for it. We may just be, maybe just some other type of optimization. So that kind of will just blend into the tools. And some of the things I'm going to talk about today will do that. Now, there will be some areas where you will definitely be interacting with AI and see an area that it applies to your day-to-day. And the things that we're really seeing right now are a couple of things. First off, debug. So weeding through all the data to help root cause where a problem is. The other one would also be just optimization. How are we making sure that we're spacing jobs out the right way on the farm, that we're maximizing coverage, all of those types of things. So across the board, there's a lot of capability here and a lot of potential. Now, this was said earlier as well, the engineer in the loop. This is really key. So yes, verification is a big data problem. We're creating tons of information, whether it be coverage information, test pass, fail, how long those tests ran, all of the various databases that go along with that. There's all that information. Weeding through that, that's a challenge. AI is really good at that. The other side is there's a certain level of expertise and just experience working with things when you're digging into the problem that the human is absolutely required for. There's a level of intuition that builds over time, and you just really get to know certain blocks of code and systems and how it works. There's no replacement for that. AI just can't do that. But if we can use AI to help work with all the data, then we can catalyze the engineer to be able to do more and work through that, be more productive, be faster. And that's really what we're seeing. So I'll go into a lot of these technologies that we're working on. So first, to just kind of present our AI platform, it is the Verisium AI-driven verification platform. There are several aspects to this. There's your traditional debug, planning, job submission, all of that's inside of there. And what's really interesting is all of the verification data is essentially living around Verisium. So our coverage databases, our test plans from previous projects, everything that's changed over time, how long a test runs, what seeds I ran, all that information is buried deep inside of this. And by taking that information and using special, like essentially add-ons, the little apps that plug into it, we can then utilize that information and help the engineer. So we're seeing a couple of areas here. I kind of mentioned a couple of them earlier. One is debug, the other being optimization. And then also I'm going to talk a little bit about some ongoing research that we're doing with copilots and some of the things we can do with generative AI. So this is a good starting point. Kind of remember being at a DAC on a panel a couple of years back, I think with Brian Bailey, and we were talking, and one of the things that really came out is we've seen a lot of innovation in verification, but not a lot of innovation necessary in just flat out debug. How do I get more efficient at debugging? How do I find the root cause? So this is one of the first things we've been working on for the last several years, and it's really applies into that case of, say, just take a standard flow. Engineers are checking in code. It's going into regressions. You're collecting data, pass, fail, error messages. Then you're kind of working through all of that system. So the first thing that you usually do, and back when I was wearing my verification hat, I used to just do a simple grep, grep UVM error messages and try to bucketize my failures. The first thing you're trying to do is like, okay, I had 50 failures. Do I really have 50 bugs? Likely not. There's some kind of bucketization that needs to happen. I need to figure out how I'm going to divide and conquer, which ones are the highest priority. This is an interesting area where AI can help. We can actually take a look at those failures and start looking at the various characteristics of why the failure happened, what time it happened, what the error messages were, what code change happened. We can learn all that information. As the engineer works through that, we actually can present a list of buckets. Here's how we think these should be classified. And then the engineer works through that, and we can kind of reinforce that and do a little learning from that as well. So we can say, okay, now this should go here. This is a completely different bucket. All that information can be learned. And as your regression evolves through your project, it gets smarter and smarter and smarter. The next side of it is once you've kind of figured out where your key problems are and you know, okay, this is the hottest bug, I've got to work on this. And now you need to figure out what happened. When did that code change? What broke it? Was there a check-in that broke this? I've got to narrow down that scope. Now, if you're the only one working on it, it's not that big of a deal. But if you have a piece of code where tons of people are checking in all the time, some check-ins may be related, others may not, in a big team, this can be really ugly to sort through. So again, great place for automation using AI. We can go in there and we can look at code changed. We kind of view this as a high-risk change. There was a lot of disruption in this file, and we can make some educated guesses about, we think this might be where it happened. But then, better than that, we can go in and reproduce all the check-ins and only the ones that matter and go and narrow down the scope and say, yep, this is the last test that passed, and here's the first one that failed. So now you've sorted through all that noise. That just is a big time saver. Now, the next thing you usually do, and I remember doing this, is I'd pull up a probably before the days of widescreen monitors, but you'd have to pull up a couple of monitors and have waveforms or code on each side, start diffing and say, okay, what changed? Painful. Ultimately, code moves around, you add comments, you add some other noise in there, has nothing to do with the functionality. You need a semantic diff. So how do I go in there and say, okay, what really changed? Where were most of my changes? What areas should I focus in on? Again, another great use of AI. We can look at that and we can kind of filter that out. Say, okay, here's where the code was changed. This one looks really disruptive. You might want to start here. And then finally on waveforms, kind of the same thing. You're looking at waveforms side by side, trying to diff and go, okay, where did my signals? Well, actually, first off, what signals started to change? Then your timestamp, where did that change? And then what if it's a test that actually varies? Maybe the startup sequence varies and it happens late in the test and that moves. It's just painful. So with AI, we can actually go in and start looking at the behavior of these signals, what started change, what looks interesting, narrow down the scope and say, okay, yeah, you had 100 signals in this module, but only these 3 look like they did something different. And oh, by the way, here are the timestamps where they did this different thing. So we're not saying, hey, here's your error, but we're saying there's likely something going on here. Now, what's really cool about this is take this scenario. You can run all these tools individually and you can do them, but let's say you run your regression, you go home for the night or the weekend, whatever it may be. You come back in the morning, all these tools were batched off, and you just really walk in and there's your debugger with your code and your waveforms, you're ready to go. So the reality of this, and we've had customers talk about this, is that you can go in and just save days, if not a week of effort, trying to narrow down the scope and just immediately go start looking at it. And then, of course, you still got to do some work to root cause it and figure out what happened. But you didn't have to go through all that painful stuff of kind of trudging through all that code and so forth. So that's one aspect. So, and this is something, that's been out for a while and it's showing a lot of promise. Now, there's another side to things that we can do with AI, and that is kind of getting into optimization. So I'll introduce Verisium Sim AI. And again, another great technology. Simulator vendors for years have always been, how do I make the simulator faster? You get a 1% here, 5% here, a little over and over. It's how do I make that big fundamental leap? So take a regression. Say that regression takes a week to run. Maybe there's thousands, tens of thousands of tests in it, and you get some coverage number, 92%. The reality is when I ran that regression, I was rolling the dice the whole time because I'm generating random numbers. I'm throwing different seeds at it. I probably hit some of these bins over and over, tens of thousands of times. I don't care. That bin's covered. I'm done. I care about the bin that was hit 3 times or the one that was never hit at all. But I'm still spending all this time revalidating the same thing over and over again. So imagine taking that regression and running it again, but doing it super efficient. So I don't just kind of roll the dice, and I'm being very thoughtful about where I'm directing the solver to go and hit my coverage bands. So then all of a sudden, instead of taking a week to run a simulation, maybe I can drop it down to a night or a couple of days. So that's a real big improvement in efficiency. I'm not getting anything I haven't already done. That's one thing about machine learning models is they're great about learning what you did in the past. We're not going create here. We're doing the same thing. We're just doing it very efficiently. So that's regression compression. Does some great things. I've seen some great numbers. Qualcomm actually was at Cadence Live and did a paper on this, and they saw in real life on a real project some awesome numbers. Now, there is another aspect of it. Actually, there's a couple of more aspects. One is some pretty good scenarios. Say you have a block of code you're working on. Maybe you're developing a new module, or you just got a new code drop, however you want to look at it. And you're concerned about it. You really want to beat it up. So you could also use this technique to go and just saturate that and do a lot of testing in that one area. So we call it soak testing. It's another use of this AI model. And then kind of the holy grail of it all is I'm at 92%. How do I get to 100%? Well, the way we do that today is we use engineers to go write tests. Effectively, we're writing directed tests. We're taking our constrained random test bench and we're starting to tweak it, get really over constraining and try to pinpoint it and have it go into certain spots. So that takes a lot of work. Now, I'm not saying that AI is going to solve that for us, but it can get us part of the way there. So we're adding some additional algorithms on top of this that help us go into certain areas of the design and spend more time in there and start building out so you can get some additional coverage gains in there. So we're actually talking about maximizing coverage. That is a less test that your engineers actually have to go and write. So especially when you use the engineers writing tests and you're retraining models, all this can kind of be feedback off of itself and just continue to grow the knowledge. So that's SimAI. Now, we're also applying this to formal. So for instance, our formal AI solution, what it does is it takes our formal tools and it builds a model and it's watching and learning from how we actually orchestrated the process of solving those proofs. You know, what engines worked best and got us there, so we can infer that information. Other things it's looking at is, let's say you're doing, again, code check-ins and you have these properties you've already verified. But if you can validate that the cone of logic feeding those properties has not been impacted by that code change, there's no point in having to go do it again. So we can use the learning in the system to actually figure that out and be very fine-tuned on the formal side as well. Just checking time here. All right, so kind of building on this, if you look at kind of SimAI, I kind of view autofocus as kind of a variation of that, but it's a little bit different technology. So let's say we're working on a large SoC, we have our regression, that's running great. And I have a couple modules that changed. And the reality is I don't need to rerun that whole regression again. I want to cover those modules that I just recently checked in or maybe got a new drop on. So what autofocus can do is it can understand, basically it learns as you run your regressions, which tests impact those modules, potentially which cover groups are related to those modules, which constrained random variables are related to those modules. It gets all this information, and then it can use that to build its own targeted regression. So with this, I can say, okay, I've changed this code. I want to, instead of going build a special regression just for that, where someone has to manually figure out which tests are the right ones to run, I can just have the tool and say, I'm really interested in these, go and do it. This could be automated as well. Maybe you say, okay, I just have the tool constantly watch and see where I have a lot of code changes, where I have a lot of disruptions in my design. I want it to have it automatically focus and take care of that on a regular basis. So it's always going and wringing those tests out. So with that, again, you're going to just essentially have high coverage there. Hopefully your coverage model is really well defined, and that's helping you find any potential bugs that are out there. The jobs that you're running. So say you're running something like LSF and you just kick off jobs, have a big regression, it just runs. That's great. But it's not really thinking about what is the best way to organize how those tests are spaced out, which sockets they run on, how long do the tests take to run, what type of memory constraints they have, what type of CPU does it need, all that information. Imagine as you're running regression, we're collecting all this information and we're building a model from it as well. So that when you say, okay, I want to go and kick off my jobs, but I wanted to absolutely hit the fastest possible wall clock time in getting my regression results. So you can kick this off and basically constrain it with, here's the number of sockets you have, here's the test I want to run. You figure out how to space it. I'm not going to worry about that. Let the tool go off and take care of it. So again, this is another one we're seeing some really impressive results on. You can get shorter regressions. There was one customer I was talking to recently. What they were able to do is they had a different constraint. It wasn't so much about I need to run shorter. I need to use less sockets, but keep my time to they had some other things they needed to run those other sockets. So they were able to constrain the engine down to basically find an optimized solution, and they dramatically reduced the number of sockets they needed. So what you can imagine this does is you have long pole tests and short tests, and it figures out how do I space these so that I just get through them as quickly as possible. So if all your long pole tests are blocking all your short tests, you're never going to get through it. But if you can space them differently, then you can actually get the kind of throughput that you need. All right. So let's talk about generative AI and where this is going. So I think we talked a little bit about this. It's really hallucinations. So it would be awesome if we could just open up something like ChatGPT and say, hey, I need to write some properties. I'm developing an arbiter, and I need to make sure it's round robin and fair. Awesome. The tool says, great, I can do that. And with all the confidence in the world, it spits back some code. And you're like, yo, I think you said exactly this. It's if it has the way it comes back to you, it's just so, yeah, no problem. Reality is there's no check there. So we don't know what we're getting. And I've played with this, and sometimes you get really awesome things. And you're like, I can't believe it did that. And other times you're like, oh man, I don't know what it's thinking, because it's not thinking. So that's the reality. And I've even had cases, I was playing with some Python and working through it, and it kept giving me the same wrong result over. And I say, no, that's not right. You need to do this. And it gives me the same thing again. Here it is, all again. It's great. It gets in these weird loops. So LLMs, they're cool, but I think they really need to have some additional input to make them be effective. So anyway, what this thing ended up doing was creating a case where all the requests were granted at the same time. Well, that's definitely not an arbiter. So that's not going to help us too much. So how do we fix this? Well, RAG. So RAG is really cool in that you're not going and training on this data. You're giving it the actual data. So, and it has context from which to pull. So I kind of like, in a former life, I did PCI Express. I worked on VIP. And when you worked on VIP, it was very challenging because there was always a piece of IP involved. That had a manual. Your VIP had a manual. Then you had the PCIe spec, which was over 1,000 pages. So all three of those things were written by different people in different ways, and finding the results that you needed was just very challenging. But to think now that you could actually have those as inputs using RAG, and now you can use the LLM to converse with the tool, and it can go and then do a very smart search and get the information you need, formulate a response back to you that's useful. So with that, that's really what we're using, is kind of a loop here where we have that context in a database that we're pulling out and extracting. And that database could be anything. I mean, it could be Jira tickets, it could be past test plans, any number of things. But the reality is it's real data. It's extracting from that and giving you a response back that means something to you. So here's a potential application of this. Let's say, kind of going back to that earlier case where I want to write an assertion and define this arbiter. How do I go about doing this? Well, take LLM. You have the natural language processing in there. It's all written in English. It understands what you're asking. Then you have all your design information in there as well. So your specs are there, everything that's related to it, as you've gone through the process of developing it. And it could be years of data, iteration after iteration, next gen products all built on this. Then you have a copilot, and you're working with the copilot, you send your prompt in, and it goes in and develops some properties. Great. So you get your property back, Now you have to do a quality check. You can't just say, oh, it's good. So you got to look at that. And there's a combination of, off-the-shelf tools, like we could use Jasper, do some checks on those properties, make sure they're reasonable. But excuse me, ultimately, it's the engineer that's sitting there driving the copilot who's going to work with this, and it's going to guide it. So if you get a garbage property out, the engineer will flag that and work with training it again to kind of reinforce where it should be doing. And over time, this just gets smarter and smarter and more accurate. So that's one potential application of this. Now let's take this a step further. So think of your whole team is utilizing this. Your specs are there. All of your documentation from your IPs are there. All the design review information's been there. All that's sitting in a database. Now we use the real language LLM to go in, formulate our questions. You may be sitting there doing a design review and you're looking something up and you need to pull that up. That's great. You could go in and say, I need to create some assertions. Awesome. One thing I really like is verification plans. I don't think anyone enjoys writing a verification plan, but they are a very necessary evil. And without them, there's no roadmap to completion. So what if we can take all the plans you have in the past, pull that data in, and have this excellent starting point as a template to move forward. So it kind of just pulls everything you've done in the past, learns from that, and gives you a really good starting point. So you only have to kind of clean up the plan and kind of tweak it to your needs. So, and you can imagine as well, as you work with it and it learns from your inputs, if you're doing a good, if you like what you're getting out of it and it's learning that, it's going to get you more and more on target each iteration through the tool. The other thing we could potentially do is have an agent that helps you generate some UVM code. Maybe you need some test bench code. I need to build a checker for this arbiter. Of course, with anything that's auto-generated, you still got to check it. So there's always that aspect. But it shows a lot of potential. And here's kind of the vision that we have. And this is something that we're working with customers today. You have a front end, that's your copilot. And you have all your database underlying. So everything that's related to your design is there and past designs. With this, you have all the spec information. So I can go off and build my assertion properties with it. I can do scripts. Maybe there's some kind of setup script that I need to run a tickle script for Jasper. It can go off and create that for you based on things you've done in the past. Also documentation. So, I'm going back to this PCIe example. Maybe I need to do something with byte enables, and I can't quite remember how that needs to be set up. I could do a search on that, and it can give me good contextual information about that. I can use that information and then do something with it. Debug. This is one that I think looks really promising. I think everyone's had this case. I want to find a signal that was doing this at this time, and then another one that was doing this. Maybe you can define some kind of relationship. And then the tool goes in and says, here's your two signals, highlights it in your waveform viewer, and then you can start debugging. So I think there's a lot of potential here. Like I said, we're already seeing excellent progress around it, but these will eventually be tools that will be in your hands. So with that, I'll just kind of wrap up and just kind of tie it back to the Versium AI verification. So just kind of keep in mind, all your data is here. We have the ability to mine that data, use AI algorithms on it to do efficient things, especially weeding through the noise, getting through all that data to make your life a lot simpler. And doesn't mean we're taking the work away, it just means you can get more of it done. So, all right.
Perfect. Thank you, Paul.
Thank you.
We do have time for one question. If there is a question in your audience, just put your hand up and we'll come around with a mic. Otherwise, there is one online that I can ask. There's one online. How far can I rely on LLM as best design practice is concerned? So,
okay. Yeah, so I personally wouldn't rely on the LLM, but LLM coupled with RAG, I think does get you a good bit of the way there, because but it's still going to depend on the data that you have in the system. So if you have really good specs, you have really good history, and you've built this up and you've been diligent about making sure all of that's up to date, then you can get some good quality out of it. But there's no, at least today, guarantee that 100% correct that comes out of it. So that's why you have the engineer in the loop. The engineer has to be there and use their experience to know if what you're getting out of it is reasonable. You still have to verify it.
I think I'm going to end on that positive note because we've all still got a job, which is
Exactly. There's still a need for us.
Okay, so thank you very much to our three speakers this morning, Hemendra, Vijay, and Paul.
Thank you.
We're going to go into a half an hour break now. Encourage you to go to the booths and look at. Paul will be on the Cadence stand, but there's other stands as well. That's going to go on for 30 minutes. Then if you want to, in here we've got three speakers on RISC-V. So this is all RISC-V in here. It's session one is Doug Smith signing off with Formal. Doug Smith from Doulos, of course, is known as Mr. Formal now, apparently. So Mr. Formal will be in training session one. And if you want to know a bit more about UVM for AMS analog mixed signal verification, then you've got a remote presentation from the UK from Peter Grove and Stephen Holloway. And that will take us then into lunch at 12:30. But enjoy a 30-minute rest. There's more refreshments. Okay, and please be back promptly at 11:30 for the next round. Thank you.